Welcome to Toddcast number 41. So they're going pretty quick. So for 41, we're going to start looking at alkynes. So this is slowly transitioning from alkene chemistry, where we added to a pi bond, into alkyne chemistry, where guess what? We'll mostly add to a pi bond. So the difference of a double bond and a triple bond will be slight in terms of reactivity, but we're still going to be looking at pretty much the same reactions. So if you learned your alkene reactions really well, this chapter should be, I won't say easy is the wrong word, but less stressful than what the alkene learning was, because you're just doubling down. You're learning similar things, but there'll be a few nuances. That said, I will go ahead and start into it by considering what an alkyne is. So alkanes, everything's sigma. Alkene, there's one pi bond involved with a sigma bond combination, so you have a double bond. In alkyne, you have a sigma bond with two pi bonds between the same carbon, so you end up with a triple bond. So just a reminder, sigma, pi, and pi. Pi bonds are weaker than sigma bonds, so the reactivity with an alkyne is in first one of the pi bonds, and then when it becomes an alkene, there is an outside chance that alkene will continue to react. The simplest of our alkynes, you have to have at least two carbons to make a double or triple bond. So minimum of two carbons, H on each end. Notice it's 180 angle, a linear compound. And that's because if you recall, if I look at this, each carbon has an sp and p, three p orbitals and an s. For every pi bond, you're going to lose a p. So what remains is sp hybridization. Same thing with the third carbon, or second carbon, I should say. You lose one for a pi bond, one for a pi bond. Those are gone, and you end with sp. sp, 180 bond angle, linear alignment, short bond. Okay, so I have that notion. The other thing you should also note is that the alkyne carbon-hydrogen bond, the terminal alkyne, this one they're both terminal because there's only two, is the most acidic of the carbon-hydrogen bonds, not counting other heteroatoms influencing it. So we're just talking about hydrocarbons, just purely hydrogen and carbon. The alkyne bond is the most acidic. This pictorial representation, I don't know how much it helps, but if we have a carbon here and a carbon here, the H is perfectly linear. This bond is here, can represent it as this alignment. So a triple bond holding together, bond angle of 180. Okay. Length, they're actually relatively short. So a carbon-carbon bond, we sometimes say is around 1.4 to 1.5 angstroms. The carbon-carbon triple bond is down around 1.2 angstroms, notably shorter, therefore notably stronger than other carbon-carbon bonds. So the triple bond stronger in double, double stronger in single. So I want to go ahead and look at the possibilities. So here's just a skeletal backbone where we have carbon-carbon and two things attached, carbon-carbon, two attached, carbon-carbon, two attached. It can, as we mentioned, be terminal at both ends, but then it also can be substituted at both ends. So we have CH3 and CH3 at each end. There's no terminal hydrogen, so it's no longer considered an acidic compound. Or acidic is a bit of a stretch. Your pK is around 26. That's awfully high, so I should be calling it acidic, but I should say it no longer has an H that can be easily removed, and easily, even then I'm now doing the language game, but removed with a strong base. An alkyne can lose it, alkane, much more challenging to lose an H through an acid-base reaction. This is called 2-butene because the double bond starts at 2, finishes at 3, no matter which way you go from. Next one, longest chain is 1, 2, 3, 4, 5, 6. So counting from the right, third carbon, counting from the left, third carbon. So either way, the triple bond starts at 3, from carbon 3 to 4, no matter which way you go. So it's 3 hexyne for the 6 carbons. And then finally, 1 pentyne, implying that the double bond starts at carbon 1, goes to carbon 2. Now pentyne, unlike the other two, has a terminal H, which means you can deprotonate it. So the pK of this proton, again, we did the 5 to 10, 15, 20, 25 rule. So we said these are roughly 25. Reality is they're a little bit closer to 26. Not really a big ordeal of a lie that I told you when I called it 25. It's in the neighborhood. want to revisit what we did early in the semester and just talk about how the orbitals are lined up. So the sigma bond between the carbon and carbon is set up here with a little overlap here, set up here with a little overlap there, and then these other orbitals are going to line up with the H. So I have the density shared between the carbons and the density shared with the hydrogen. You also have a pi bond. I'm going to call this, let's say, the XY plane. So if this is a PY, it's straight up and straight down. And then also in the Z direction, let's say. So let's say X is here, Y is this, and Z is coming in and out. So this would be in the XZ plane. Then this pi bond is here, this one's pi bond's here. So when you put them together, you can see there's a vertical and a horizontal pi bond or planar pi bond or relatively planar pi bond. So hopefully that visual makes sense. So all the electron density in acetylene, the sigma bond between carbon and carbon, one pi bond, which we draw vertical, one pi bond that we draw horizontal. And as far as reactivity goes, either pi bond can be reactive. There's no preference for one over the other. So again, breaking into individual components, here are my pi bonds, kind of confusing. Here are my sigma bonds and the appropriate p orbitals we're dealing with. I've decided to call it px and py and make the z along that axis. So already I've changed from up here, which shows you how important it is in terms of knowing x, y, and z, which it's arbitrary, completely random. I chose x and y to be x to be vertical, y to be horizontal here. I chose differently up there. I will never ask you to identify a certain plane other than to note that there is px's and py's. Relative acidity, again, alkynes are more acidic than alkenes. Alkenes are more acidic than alkanes. The pKs are roughly 26, 40, and 46. 49, excuse me, sorry. So note that this is in the 25 range. So the 5, 10, 10, 10, 15, 20, 25 rule still holds for the most part. Okay, we have our background information. So along the things that we've already done, and it was a subtle thing we did in chapter 7, but we're talking about nucleophiles. And one of the nucleophiles that slipped in there was the deprotonated alkyne. So a terminal alkyne, again, on an sp carbon has a pK of 26. So if you add a strong enough base, and we've been dealing with some pretty strong bases in some of the previous examples. So if you add something along the lines of LDA where N has a negative charge, or you add something with a carbon with a negative charge, even stronger, we'll call it butyllithium, you can deprotonate this carbon and make it a really good nucleophile. So this nucleophile has this lone pair that is now free to attack an Rx, X being some halogen, and kick it out. So let me erase this. So this great nucleophile can now attack, in this case, H3C, excuse me. So it can attack that carbon and dislodge the I through an SN2 mechanism. SN2 reaction. So you end up with your final product. So strong base, LDA, which has a negative on nitrogen, lithium amide or amide, can also be sodium amide, potassium amide. You can use that, or you can use butyllithium, where you have carbon with a negative charge and lithium holding in place. Any of these will work. They're all strong enough. I'm going to choose LDA probably most often, just because it's readily available. But be aware that all three of these are strong enough bases. So these three are all very strong bases. We can deprotonate an alkyne. Okay. These relative pKa, and note the pK is of the conjugate. So it's even a weaker conjugate acid. So that means the pKb is what, 14 minus that, which means negative 23, plenty strong enough to pull off something. So because this is a weaker, the conjugate acid LDA is weaker than the alkyne, it'll work. This one is around 38. So again, very strong base, but the conjugate acid, note that this number is the pK of the conjugate acid, this pK of the conjugate acid, this is the pK of the conjugate acid. These are all weaker acids, so their conjugate base will be strong enough to pull off this H. This goes back to chapter 3 when we were trying to decide what the relative pKa's were and whether the reaction was favorable or unfavorable. This is a major part of why we did it, to help generate, for instance, an alkyne anion. So if we consider this reaction, take some alkyne that we just deprotonated, that's this one here, and then we add it. So what we're trying to show is a CH2 group with, I guess, two CH2s in a row, and a CH3. So basically, 4-carbon chain. When I add it to this, it's going to deprotonate. So this is my butyl lithium. So that's what this compound is. When I add it in, it's going to deprotonate because your respective pKs are 26 and 49. And as you know, it goes from weaker to stronger, or stronger to weaker. Can't remember. So hopefully you know. It goes from the stronger, more reactive species, less stable species, always to the weaker one. But it ends up going from the lower number to higher number is what I was thinking. So I apologize for being asleep at the wheel for a moment there. But the stronger acid gets deprotonated and turns into the weaker acid. So that's a highly favorable reaction. So it will tear that proton off. So 26 and 49. I'll leave it for the prettier picture. Say it goes in that direction. Stronger going to weaker. Okay, we revisited our acid base. Typical synthesis then. If you start with something like acetylene, so we're going to make the alkylide nucleophile. Wow, it's tough to say, but we're going to make this species. We're going to deprotonate it with butyl lithium. We're then going to add that via an SN2 reaction to some alkyl halide. I've chosen a primary alkyl halide to ensure that we have some sort of SN2 reaction. This great nucleophile comes in, kicks out the iodine, and we've added one R group. So we deprotonated again because there were two H's to choose from. So we deprotonate the second one. When I do that, I make another great nucleophile. That great nucleophile will attack a different. So I've tried to signify this is 1' and this is 2', meaning in the end, I get one R group here, another R group there. So you can build a specific alkyne. If only we could turn an alkyne into an alkene, then I could add in all those reactions I learned in the previous chapter to build on this pool of information. And guess what's going to happen? That's exactly what we're going to do. We're going to learn the art of turning the triple bond into a double bond and opening up a whole new avenue of synthetic pathways. Okay. So to get an alkyne, we've learned how to manipulate an alkyne, deprotonate it, and put on an R group. Part of the things that are part of the process in covering the big picture, we have to learn what reactions alkynes do, but we also have to learn how to make an alkyne. So I'm going to talk about a double elimination. So we know an elimination reaction generates an alkene. So if I do it twice, so if one elimination generates 1 pi bond, a double elimination will generate 2 pi bonds. So in the exact same way that we had to worry about anti-addition, we have anti this H to this Br, or this H to that Br. If we line things up the right way, both the BRs and are anti, so they both can get eliminated. That's what we're going to count on. Introducing a new word, and if you know the word Gemini from some, I guess, astrology, you know that that means twins. Or if you happen to speak like a Latin-based language, such as Spanish, gemelas and gemelos, will mean twins. So hem, that Latin lead should tell you these are twins, maternal twins. They come from the same mother carbon right here. So I add a very strong base with heat, like we do in terms of elimination reactions. Strong base and heat is going to eliminate. And I don't know which to eliminate because we have two options. And so in the end, it doesn't really matter if we did this one and this one, H and Br end up there, or if we did that one and that one, H and Br end up in the same spot. So it ends up being kind of a moot point. We're doing elimination, could be either one, because they both end up anti. And your most stable conformation with bulkiest group, anti to the bulkiest group. So carrying out this with a little more heat. So keeping it warm, again, like it mentions, H perfectly anti to this because it's now a vinyl bromide, so the orbitals are lined up just perfectly for elimination. You can do it one more time. So the dibromo species is going to form a double elimination product of an alkyne. Notice the CH2, CH3 is there, the CH3 is there, and the two carbons are now forming the triple bond right there. Okay, not bad. If they are not on the same one. They're not geminal, they're neighbors. They're in the vicinity of one another, so they're vicinal. Or again, if you happen to speak a Latin based language such as Spanish, vecino, meaning neighbors. So they're this inol. So on neighboring carbons, you can get the same thing, but the lining up might not be as convenient for both of them. So in other words, I have to rotate to make sure that one's anti, that one's anti. It worked out well in this case, but if you have the enantiomer, you might only be able to get one elimination at a time. It really doesn't mean that much because you're still going to end up with the same situation with a vinyl bromide, which is going to be able to be eliminated. So whether they're geminal or vicinal shouldn't make that big of a deal. I will take anything that you do if we have a synthesis where you have to generate a triple bond. We start with two on the same or on neighboring, that's fine. I chose bromine because it's good a leading group as any, but if you chose chloro or iodide, you're going to be fine. Okay. The key, both reactions to both, I should say, is the second elimination. So as you keep the heat on, keep the base at high enough concentration, you can tear off a second H. So because this is stoichiometric, this base picks up a proton permanently, becomes methanol. You have to have two equivalents of base, one for the first proton, one for the second, to make it go. If you shortchange it and don't give it enough base, it will not go all the way to completion. So, and the fortunate thing, because of the increased acidity of the H that is on the adjacent carbon to the vinyl bromide, you always end up getting the second pi bond formed in the exact same spot the first one formed. So you always end up with an alkyne as opposed to what's called an alene, where you have two consecutive double bonds. Kind of tricky to get that one. But this one, if you start with geminal or vicinal, you'll end up with an alkyne if you do enough equivalents of base. Well, that ties off the lead-in. This is how we make alkynes, and just a revisit of what alkynes are structurally. We're going to now pile on a ton of reactions, and just to give you a heads up, I'm probably going to go a little bit faster, so you may have to turn down the speed if you really need to look at everything. But I'm counting on the fact that because you did the alkene reactions, double bond reactions so well, the alkyne reactions will be pretty easy. So thank you, and I will see you at the next podcast. Bye.